Assalamu alaikum students. In this lecture, we will discuss the magnetization current in a real transformer, and also we will discuss the current ratio on a transformer and the dot convention. The diagram of a real transformer is shown here. As you can see in this diagram, as we have already discussed, this is the primary circuit and this is the secondary circuit. As we know, when we will connect the AC voltage source across the primary circuit, then the current will flow in the primary circuit, as you can see in this figure. Even the secondary circuit is open because there is no connection between secondary winding and primary winding. Due to this, due to the primary current, according to Ampere law, flux will produce in the real ferromagnetic core. When the current will flow across the primary winding or across the primary circuit, then according to Ampere law, a flux will produce in a real ferromagnetic core. This is the flux and this is the real ferromagnetic core. This primary current, as you can see in this figure, this primary current is basically consists of two components. The first one is magnetization current. We represent the magnetization current with Im, and the second one is the core loss current. We represent the core loss current with IH plus E. H means hysteresis and E means eddy current. First of all, we will discuss the magnetization current Im. After this, we will discuss the core loss current, that is IH plus E. The magnetization current Im is the current which is required to produce the flux in the transformer core. That is, the current which is required to produce the flux in the transformer core. This current is called the magnetization current. And the other type of the primary current is the core loss current. The core loss current is basically the current which is required to make up for hysteresis and eddy current losses in the core. As we have already discussed, there are two types of losses occurs in the core. The first one is the hysteresis losses and the second one is the eddy current losses. The combination of hysteresis and eddy current losses is called the core losses or iron losses. Due to these losses, there will be some current lost. This lost current is called the core loss current. We represent the core loss current with IH plus E. H means hysteresis, E means eddy current. The current lost due to hysteresis and eddy current losses is called the core loss current. So these are the two components of primary current. The first one is the magnetization current and the second one is the core loss current. Now we will discuss the shapes of the magnetization current Im and the core loss current IH plus E. That is, are the magnetization current and core loss current the shape of these two is AC or DC. Now we will discuss the behavior of or the shape of or the waveform of magnetization current and core loss current. First of all, we will discuss the shape of magnetization current. The shape of magnetization current is AC or DC, etc. First of all, we will discuss the shape of magnetization current IM. As we know, the average flux in the core is 5 in the core is across the primary winding is average flux across the primary circuit is equal to 1 over NP integral of Vpt into dt. NP means the total number of turns across the primary circuit and Vpt is the applied voltage across the primary circuit, and phi dash means the average flux due to primary winding. And as we know, according to Faraday law, induced voltage is equal to N into d phi dash over dt. After taking the integral of both sides of this equation, we can derive the equation of flux, that is the equation of average flux. The equation of average flux across due to primary circuit is 1 over Np integral of Vp into dt. Now let, if the applied voltage across the primary circuit is Vpt is equal to Vm cos omega t, let the applied voltage across the primary circuit is, that is the value of the Vpt is Vm cos omega t, that is the shape or the waveform of the applied voltage is in cosine form. Now, so putting the value of Vpt in this equation, that is the value of Vpt is equal to Vm cos omega t, in this equation we will get flux, average flux across the primary winding. The average flux across the primary winding will be equal to 1 over Np integral of Vm cos omega t dt. Here we just put the value of Vpt is equal to Vm cos omega t in this equation. We get average flux due to primary circuit is equal to 1 over Np integral of Vm cos omega t dt. Now, after taking the integral of cos omega t, we will get the average flux due to primary circuit is equal to Vm over omega Np into sine omega t. As we know, the integral of cos is basically sine. Here we just solve the integral, we take the integral of cos omega t, and the final equation of the average flux due to primary circuit is Vm over omega Np into sine omega t. So this is the final equation of the flux due to primary circuit, and this is the applied voltage across the primary circuit. As you can see in this equation, the applied voltage is in the cosine form and the flux produced due to primary circuit is in the form of sine. The flux is in the sinusoidal form and the applied voltage is in the form of cos omega t. It means the applied voltage and the flux in the transformer are not in phase. The applied voltage and the flux are out of phase, that is the phase difference between the applied voltage and the average flux due to primary circuit is 90 degree. Both are not in phase, as you can see in both equations. The applied voltage is basically in the form of cos, and the average flux is basically in the form of sine. So these two equations are very important to determine the shape of the magnetization current Im. These two equations will play very important role to determine the shape of the magnetization current Im. As the applied voltage across the primary circuit is equal to Vpt is equal to Vm cos omega t. If the value of the t is 0, in case of t is equal to 0, cos 0 will be 1. As we know, the value of the cos will be maximum at 0. When the value of the t will be 0, then the cos 0 will be 1. So therefore, the shape of or the waveform of the applied voltage will start from the maximum value. As you can see here, this is the shape of or the waveform of the applied voltage. When the time will be 0, then the value of the applied voltage Vpt will be maximum, because when we put the value of t is equal to 0 in this equation, cos 0 will be 1. After the multiply with Vm, then the maximum value will be Vpt. So therefore, at time t is equal to 0, the value of the Vpt will be maximum, and at the angle of 90 degree, then the value of the Vpt will be minimum, that is 0. And similarly, at 270 degree, the value of the Vpt will be 0 as well. This is the waveform of the applied voltage. As we have already derived the equation of average flux when the applied voltage is equal to Vm cos omega t. The equation of the due to the primary winding or primary circuit is Vm over omega np into sine omega t. As we have already derived this equation, when the applied voltage will be in cos form, then the average flux due to primary circuit will be in the sinusoidal form. Now, by putting the value of t is equal to 0 in this equation, the waveform of the average flux due to primary circuit will start from 0, because when the time will be 0, the value of sine 0 is 0. When the value of sine 0 is 0, then the waveform of the average flux due to primary winding will start from 0. At 90 degree, sine will be maximum. At 180 degree, again the value of the average flux will be 0. At 270 degree, the value of the average flux will be maximum but in negative direction. Again at 360 degree, the value of the average flux due to primary circuit will be 0. So this is the shape of or the waveform of the average flux due to primary circuit. This is the waveform of the applied voltage in the primary circuit. So from these two equations, from these two waveforms, and now as you can see in these two waveforms, when the applied voltage will be maximum, then the flux will be minimum. When the flux will be maximum, then the applied voltage will be minimum. That is, the phase difference between applied voltage and the flux is 90 degree. As we have already discussed the relationship between flux and magnetomotive force, when the magnetomotive force F is equal to N into I, when the magnetomotive force, that is the value of the current, will increase, then the magnetomotive force will increase, When the magnetomotive force will increase, then the flux will increase. At the start, the relationship between the flux and the magnetomotive force will be linear. After this, the relationship between the magnetomotive force and the flux will be in transition region, and finally the relationship between flux and magnetomotive force will be in saturation region. When the magnetomotive force will increase, then after some time when the core will be in saturated region, then there will be no change occurs in the flux. So this is the relationship between the flux and magnetomotive force, as we have already discussed in detail why the saturation region occurs in real machine. In real transformer is basically works in the transition region or in the knee curve or in the region between the unsaturated and the saturated region. So this is the third waveform, the waveform between the flux and the magnetomotive force. Now we will draw the waveform of magnetization current, that is IM. As we have already discussed, the magnetization current is the current which is required to produce the flux in a real ferromagnetic core. The current which is required to produce the flux in a real ferromagnetic core is called the magnetization current. According to Ampere law, the relationship between the magnetization current and the flux is directly proportional. As we have already discussed, according to Ampere law, when the current will increase, then the flux will increase, or when the flux will increase, then the current will increase. When the flux will decrease, then the current will decrease as well. So that's why the waveform of the magnetization current will start from 0, because the relationship between current and the flux is directly proportional. Due to this, the waveform of the magnetization current will start from 0 as well. When the flux will be maximum, then the waveform of the magnetization current will be maximum as well, and so on. The waveform of the magnetization current is not purely sinusoidal, because when the core will be in saturated region, then the flux will be constant. When the flux will be constant, then there will be no change occurs in the flux even when we will increase the magnetomotive force further. In saturated region, there will be no change occurs. Due to this, the behavior of the magnetization current is not purely sinusoidal. So this is the shape of, or the waveform of, the magnetization current IM. Now we will discuss the other component of the no load current. The other component is basically the core loss current. We represent the core loss current with IH plus E. H means hysteresis and E means eddy current. As we have already discussed, it is the current required to make up for hysteresis and eddy current losses in the core. As we have already discussed, in the core there are two types of losses occurs in real transformers, that is eddy current losses and hysteresis losses. Due to this, there will be current loss. This loss current is called the core loss current. We represent the core loss current with IH plus E. H means hysteresis and E means eddy current. Now, as we know, as we have already discussed, the waveform due to primary flux is in the sinusoidal form. When the time will be 0, then the flux, average flux due to primary circuit will be 0. When there will be 90°, then the average flux will be maximum. When there will be 180°, then the average flux will be 0. So this is the shape or waveform of the average flux due to primary circuit, as we have already discussed. And this is the shape of the applied voltage VPT. The applied voltage will start from maximum value, because as when we will put the value of the t is equal to 0 in this equation, then the applied voltage will start from the maximum value. So this is the waveform of the applied voltage, as we have already discussed in detail. So now we will draw the waveform of the core loss current, that is IH plus E. There are two types of losses occurs in the core. The first one is the hysteresis losses and the second one is the eddy current losses. Hysteresis losses is basically directly proportional to the applied voltage. When the applied voltage will be maximum, then the hysteresis losses will be maximum. When the applied voltage will be minimum, then the hysteresis losses will be minimum. The eddy current losses is basically directly proportional to the applied flux. When the flux will be 0, then the eddy current losses will be 0. When the flux will be maximum, then the eddy current losses will be maximum. It means the relationship between applied voltage and hysteresis losses is directly proportional, and the applied flux or the flux due to primary circuit and the eddy current is directly proportional as well. So due to this, as you can see in this waveform, when the applied voltage will be maximum, it means the hysteresis losses will be maximum, because the relationship between applied voltage and hysteresis losses is directly proportional. As hysteresis losses is more as compared to eddy current losses. The eddy current losses is less as compared to hysteresis losses. So that's why the effect of hysteresis losses will be more as compared to eddy current losses. So therefore, the waveform of core loss current will start from maximum point, because hysteresis losses is directly proportional to the applied voltage. When the applied voltage will be maximum, then the hysteresis losses will be maximum as well, because the effect of eddy current losses is less as compared to the hysteresis losses. So that's why the core loss current will start from maximum point. When the applied voltage will decrease, then the hysteresis losses will decrease. But when the applied voltage will decrease, then the flux will increase. When the flux will increase, then the eddy current losses will increase. It means when the hysteresis losses will decrease, then the eddy current losses will increase. Due to this, the curve at the start at this point will be straight line, because at this point, when the applied voltage will decrease, then the hysteresis losses will decrease. But when the applied voltage will decrease, then the flux will increase. When the flux will increase, then the eddy current losses will increase. The overall effect will remain same. So that's why the curve at the start will be straight line. And after this, when the applied voltage will decrease more, then the overall effect of the core loss current will start to decrease. And again, when the applied voltage will increase, then the core loss current will increase as well. It means the relationship between the core loss current IH plus E and the applied voltage VPT is in phase. When the applied voltage will be maximum, then the core loss current will be maximum. When the applied voltage will be minimum, then the core loss current will be minimum. It means the relationship between core loss current and applied voltage will be in phase. So these two are the in phase, that is VPT and IH plus E. Now we will discuss the excitation current. The excitation current or the primary current is the total no load current in the core. The total no load current in the core is called the excitation current of the transformer. That is, if the secondary is open circuit, then the no load current across the primary circuit is called the excitation current. When we apply the voltage source across the primary circuit, then the current will flow across the primary circuit, and we will keep the secondary circuit is open. This current is called the excitation current. Excitation current is basically divided into two parts. One is called the magnetization current and the other one is called the core loss current. That is, the combination of magnetization current and core loss current is called the excitation current. The behavior of excitation current will be the sum of magnetization current and core loss current. As we have already drawn the waveform of magnetization current and core loss current, the waveform of magnetization current IM is shown here. As we have already drawn the waveform of magnetization current, and this is the waveform of core loss current as we have already derived. When we will add these two waveforms, the overall behavior will be equal to the excitation current. In case of excitation current, we just add the magnetization current and core loss current. When we will add the magnetization waveform and core loss current waveform, the overall behavior will be like this. At 0, the overall behavior at this curve will start from 0. The reason is that this factor is 0 and this factor is maximum because the effect of magnetization current is very greater than the core loss current. We can neglect the core loss current. The core loss current is basically approximate near to 0. The effect of magnetization current is maximum. Due to this, the overall graph of excitation current will start from 0. The reason is that the effect of core loss current is approximately equal to 0 and the effect of magnetization current is maximum, that is very greater than the core loss current. So that's why excitation current will approximately is equal to magnetization current. So overall effect will be, the overall waveform of excitation current will be like magnetization current. So this is the waveform of excitation current. Now we will discuss the current ratio on a transformer and the dot convention. Normally we mostly use core type transformer. As you can see in this figure, the diagram of core type transformer is shown here. This is the primary winding, as we have already discussed a lot of time, and this is the secondary winding, and this is the ferromagnetic core. Power source is basically connected with the primary circuit or with the primary winding, and load is connected with the secondary circuit. As you can see in this figure, the primary circuit is basically connected with the power source and the secondary circuit is basically connected with the load. There are, now as you can see in this figure, there are two dots. This is the dot number 1 and this is the dot number 2. Dot is basically used to identify the polarity of the voltage coming out of the secondary with respect to the primary. In case of transformer, we use the dot is basically to identify the voltage polarity. Now as you can see in this figure, dot is basically represent the positive end of the voltage source and undotted end of the undotted point is basically represent the negative end of the voltage source. In case of transformer, the dotted point is basically represent the positive end of the voltage source and undotted point is basically represent the negative point of the voltage source. So that's why this is called the dot convention. Dot means positive end and undotted means negative end of the voltage source. Now when the current will flow across the primary circuit, then the flux will produce. When the flux will pass through the secondary winding according to Faraday law of electromagnetic induction, then the voltage will induce in the secondary circuit. But according to law of inertia, the direction of the induced voltage will be opposite to the applied voltage. That is, the direction of the induced flux. When the voltage will induce across the secondary circuit, due to this current will flow. Due to this current, the flux will produce across the secondary winding. The direction of the flux will be opposite to the direction of the applied flux. The reason is that according to law of inertia, the charges don't want to move. When the charges will move, then the charges will generate the opposite EMF. So that's why the direction of induced flux will be opposite to the applied flux. Now as you can see in this figure, this is the flux when the induced voltage will produce across the secondary winding. Due to this, opposite flux will produce and the direction of the opposite flux will be opposite to the applied flux. The other important point here is that when the current will flow into the dotted point, as you can see in this figure, when the current will flow into the dotted point, in the dotted end of the winding, then the magnetomotive force will be positive. If the current will flow into the dotted dotted point of the winding, then the magnetomotive force will be positive. That is, F will be equal to plus NP into IP. When the current will flow out of the positive point, not into the dotted point, then the magnetomotive force will be negative. That is, F will be equal to minus NS into NS into IS. That is equal to minus NS into IS. It means when the current will flow into the dotted point, then the magnetomotive force will be positive. When the current will flow out of the dotted point, then the magnetomotive force will be negative. That is, F will be equal to minus NS into IS. So dot convention is basically used to identify the polarity of the voltage coming out of the secondary with respect to the primary. So the net magnetomotive force will be equal to F net will be equal to magnetomotive force due to primary winding plus magnetomotive force due to secondary winding. The magnetomotive force due to primary winding is positive and the magnetomotive force due to secondary winding is negative. So therefore F net will be equal to NPIP minus NS into IS. And also, as we know, magnetomotive force is equal to flux into reluctance. Therefore, NPIP minus NS into IS will be equal to flux into reluctance. As we know, in case of well-designed transformer core, the reluctance is very small, near to zero. If the transformer is well designed, then the reluctance of the transformer is very, very small or near to zero. When the reluctance will be nearly is equal to zero, then this equation will be approximate is equal to flux into zero, because in well-designed transformer, the reluctance of the well-designed transformer is very small, that is nearly to zero. When the value of the reluctance will be zero, then the overall equation will be equal to NPIP minus NS into IS approximately is equal to flux into zero. So after multiplication of 0, the overall equation will be equal to NP into IP minus NS into IS is equal approximate is equal to 0. When we will take the NS and IS into the other end of the equation, then NP into IP will be approximately is equal to NS into IS, and here the value of and the current ratio will be equal to IP over IS will be approximately is equal to NP over NS will be equal to 1 over NS over NP will be equal to 1 over A. So this is the current ratio formula on the transformer, that is IP over IS approximately is equal to NS over NP is equal to 1 over A means turn ratio. So this is the current ratio formula of the transformer. In order for the magnetomotive force to be nearly zero, current must flow into one dotted end and out of the other dotted end. So this is the very important condition for in order for the magnetomotive force to be nearly zero. So that's it for this lecture. In the next lecture, we will discuss the equivalent circuit of a transformer. So that's it for this lecture.